All right, let's dive into something that's at the very heart of our digital world. How in the world do the words we type turn into actions that a computer can actually perform? It's a fascinating journey, so let's get into it. I mean, really think about it for a second. We sit here, we type out words and symbols, and somehow that becomes a video game, a website, or the app you're using on your phone. It feels like a kind of magic, doesn't it? But it's not magic, it's actually a brilliant, layered process of translation. So, how does it all work?
Okay, so to get our heads around this, we have to start at the top layer. We're talking about the languages that are designed to be closest to us humans. These are called high-level languages, and they are, by far, the main way programmers talk to computers today.
So, what makes a language high-level? Well, it's pretty simple. They're designed for us. They let programmers write instructions using words and logic that are a lot closer to English than they are to what's actually happening deep inside a computer chip. It's all about abstraction. Basically, hiding all the messy, complicated details so we can focus on the bigger picture. And you've definitely seen what these languages can do. C++, Java, C#, these are the absolute powerhouses behind things like your computer's operating system, those incredibly realistic video games, and the huge enterprise applications that pretty much run the modern world.
And right here, this is the central puzzle, isn't it? We write in these elegant human-readable languages, but deep down, a computer processor only speaks one language, and it's the most basic one you can imagine, on or off, 1 or 0. So how do we bridge that massive gap?
This brings us to the really crucial part of this whole journey, the Great Translation. We need a way to take our human-friendly ideas and convert them into the computer's native language. This is what a computer actually gets. It's called machine language or machine code, and it's not made of words at all. It's just a long stream of numbers that corresponds directly to the physical operations the computer's hardware is built to do. This is as low level as it gets.
So, how do we get from our C++ code all the way down to those raw numbers? We use a special program called a compiler. You can think of the compiler as the ultimate translator. Its entire purpose in life is to take the code a human wrote and meticulously convert it into the equivalent machine code that the processor can finally understand and execute.
So the process basically looks like this. First, a programmer, like you or me, writes the code in a high-level language. Then, the compiler does all the heavy lifting, translating that source code into a brand new file that contains only machine language. And finally, the computer can run that new file, executing those instructions directly. But to really truly appreciate what an amazing job the compiler does, it really helps to understand the middle ground, the layer that exists between our human language and the computer's machine code. For a long time, this was a step every programmer had to take. I mean, you have to picture this. In the earliest days of computing, programmers had no choice but to write in raw machine code, just punching in ones and zeros. It was an incredibly slow and painstaking process. But then, in the early 50s, there was this huge breakthrough. Computer scientists developed a symbolic system. An assembly language was born. So instead of typing a long string of ones and zeros, a programmer could now write a short, memorable word. It's called a mnemonic. Words like add for addition or move for moving data. Now, each one of these little words corresponds directly to a single machine instruction. It's still very, very low level, but believe me, it was a world of difference from typing pure numbers. A single line of assembly code is built from a few key parts. Every single instruction has to have a mnemonic. That's the command itself, like MOV. Then it might have operands, which are just the pieces of data or the memory locations that the command will work on, and then you can add optional things like labels or comments to help keep the code organized. So we have all these layers, high-level, assembly, and then machine code. But why? What's the real benefit of working way up there at that highest level of abstraction? Okay, let's take this incredibly simple command. All this does is create a variable called x and give it the value of 5. That's it. It's clean, it's simple, and any programmer can look at that and know exactly what it means in less than a second.
And this is the magic of abstraction. That one simple, human-friendly line of code doesn't just become one line of machine code. Oh no, the compiler translates it into a whole series of instructions for the processor. Things like find a free spot in memory, convert the number 5 into binary, put that binary value into that memory spot, and so on. That's the power of these layers. One simple thought for us becomes dozens of precise steps for the machine.
So the crucial point here is that each of these layers is a tool, and you just have to choose the right tool for the job. There's always this trade-off happening between human convenience and direct machine control. And this chart just lays it all out perfectly. You could see that with high-level languages, readability is great for us, but you give up a little bit of that fine-grained control and raw speed. As you move down the ladder toward machine code, readability absolutely plummets, but your control over the hardware becomes absolute. You can squeeze every last drop of performance out of it.
And that leaves us with a really fascinating thought to chew on. For decades, we've been building better and better compilers to create higher levels of abstraction, moving us further away from the machine and closer to just plain human thought. So now, with AI really entering the picture, what's the next layer going to look like? Will we soon be programming just by describing what we want in plain English? It's a pretty wild future to think about. Thanks for watching.